Hello and welcome to the solution guide for Foghqwgads by my dad Bellal and myself, the pedaling pianist. In fact, this is also a partial solution guide for any other puzzles with a similar rule set, and we do have a few in the pipeline because, as you might have noticed, the entire grid is covered in fog, which means that the first digit can be deduced from the rule set alone, making it effectively like a really difficult given digit for any puzzles with these rules. I'll make it very clear in the description with a timestamp exactly when this solution guide becomes unique to Foghqwgads. Before I dive into it, I'd love to give a huge shout out to my dad, who is an absolute puzzling genius, particularly within the world of chess problems, but he's also helped enormously with a lot of the sudokus that I've been constructing over the last year or so, including two that got published to the Cracking the Cryptic YouTube channel under my name, so perhaps in hindsight I feel I owe him a little bit of acknowledgement for those. This puzzle, though, is absolutely not a puzzle that I have constructed with a bit of help from my dad. It's very much a joint composition of which we're both very proud. So, the rules are normal Sudoku rules, normal fog of war rules, so placing a correct digit will lift some fog and reveal some clues. Then a rule set that we're calling filler. There might be an official name for this rule set that we're not aware of. We're still quite new to it, but that's what we'll call it for now. This is the rule that says, shade some cells such that each digit in row 1 indicates the count of shaded cells in its column, and each digit in column 1 indicates the count of shaded cells in its row. For example, a 3 in row 1, column 8 indicates that there are 3 shaded cells somewhere in its column. Then we have normal Yin Yang rules. All shaded cells must form one orthogonally connected region, as must all unshaded cells, and no 2x2 square can consist of only shaded or only unshaded cells. We also have balancer lines. Along balancer lines, the sum of digits in shaded cells equals the sum of digits in unshaded cells. The lines do not branch. All lines are red, except when two lines share a cell, in which case one of the overlapping lines is coloured purple, so that's just for a little bit of clarification. So, for example, if we found out that this was a balancer line, and we also found out that these were shaded and these were unshaded, then that would be telling us that the sum of these 3 digits is equal to the sum of those 2 digits. Just to avoid the grey of the fog and the red and purple of the balancer lines, I will be using dark green for shaded cells and light yellow for unshaded cells. It's not ideal, but hopefully they are distinct enough. So let's begin. The first thing we can do is consider where a 9 goes in this column. If we put it in any of the middle positions, for example this one, then that's telling us that all of these 9 cells are shaded. We know that there must be at least one unshaded cell up here because that's no longer going to be a 9, and there must be loads of unshaded cells down here as well, and those unshaded cells will be isolated from each other because of this wall of shaded cells that we've created, and that breaks Yin Yang, so that cannot be the case. The 9 in this column must go either here or here. Exactly the same logic applies to this row, so the 9 must go here or here. In other words, we either have a 9 here or 9s here and here. In both of those cases, these 2 cells get shaded, but that's pretty much all we can do without having a bit of a deeper understanding of the filler rule set. To demonstrate this, I have prepared this grid called Secrets by Mr. E. And I've put these 17 digits pretty much randomly. It really doesn't matter where they go to prove these secrets. So I'm going to claim that whenever we have a cell whose coordinates sum to 10 or more, and by coordinates I mean the first digit in its column and the first digit in its row, if they sum to 10 or more, then that cell must be shaded. If they sum to 9 or less, for example this one, that cell must be unshaded. There's probably a concise mathematical way of proving this, but the way of proving it that I find most easy to visualise is by just kind of brute force. So firstly, we know that there will be a 9 somewhere in this column. Really doesn't matter where it goes. In this example, I've put the 9 here. That tells us that all 9 of these are shaded. We also know that somewhere along the top row there must be a 1. Again, really doesn't matter where it goes. In this case I've put it here. This 1 has already filled its quota of 1 shaded cell for the column, so these all become unshaded. In other words, the only shaded cell we could put in the 1 column was the cell where the coordinates summed to 10 or more. All of the other cells became unshaded. Now we can look at an 8 in this column. Again, doesn't matter where it goes. Wherever it goes, its quota of unshaded cells, i.e. one unshaded cell, is now filled. So the rest all become shaded. In other words, the only opportunity for an unshaded cell in this row was the one where the coordinates added up to 9 or less. Everything else was shaded. Now we can look at the 2 in this row. This 2 has already got its quota of shaded cells wherever it goes along the row, and so the rest all become unshaded. And again, we can see that the only 2 shaded cells in this column were the 2 where the coordinates summed to 10 or more. Wherever the coordinates summed to 9 or less, we got an unshaded cell. And you can see how this just keeps perpetuating. We'll next have a look at the 7 in this column. The only 2 unshaded cells in this 7 row are the 2 where the coordinates sum to 9 or less. And then the 3 in this row. And it doesn't matter that we've put the 3 in the corner, losing its religion. The logic still works exactly the same. This 3 has already got its quota of 3 shaded cells. The rest all become unshaded. And the coordinates work exactly the same. So this cell, for example, has coordinates of 3, 3, because the first digit in its column is 3, the first digit in its row is 3. 3 plus 3 is less than 10, and therefore this is unshaded. Hopefully that's a convincing enough proof, because this is a very, very important secret to understand for this solution. In fact, this gives rise to some more secrets. If we ever have a shaded domino in any row, doesn't matter where the row is, and it doesn't matter what this number is. Let's just say it's a 5, for example. Can we ever put a higher digit in either of these positions? Well, let's try it. Let's put a 6, for example, just here. Well, the implication of those 2 cells being shaded is that these 2 digits, whatever they are, when you add 5 to them, you get at least 10. Well, if they're high enough for that, then when you add 6 to them, you're definitely going to get at least 10. In fact, you'll get at least 11. And so these cells become shaded as well. And that breaks yin yang, because we can't have a 2 by 2 of all shaded cells. Similarly, if we try putting an unshaded domino in any row or column, and then a lower number next to it, for example a 4, then the implication of these 2 cells being unshaded is that these 2 digits are low enough that when you add 5 to them, you get less than 10. Well, if they're low enough for that, then they're definitely low enough that when you add 4 to them, you get less than 10. And so these become unshaded as well, and that again breaks because we can't have a 2 by 2 square of all unshaded cells. This also therefore gives us the result that we can never have any row or column with at least 1 shaded domino and at least 1 unshaded domino, because if you put a higher digit next to it, the shaded domino will grow into a shaded 2 by 2, and if we put a lower digit next to it, the unshaded domino will grow into an unshaded 2 by 2. This means we can start to look at the corner cells, and let's try putting a middly digit in here, for example a 5. Now, there is also a secret in Yin Yang, which I'm going to scroll down to here. The perimeter must consist of no more than 1 continuous string of shaded cells and 1 continuous string of unshaded cells, something like this. If we tried to break this up into 2 strings of each, like this, then there would never be any way to connect these shaded cells together without isolating the unshaded cells, and vice versa. So, if we did try putting something like a 5 down here, then all 5 of those shaded cells must be in a continuous string to obey that yin-yang secret. Then we would get all of these unshaded cells also in a continuous string, and now we can see that we've got at least 1 shaded domino and at least 1 unshaded domino, and therefore this cell has no valid fills without either creating some unshaded 2 by 2s or some shaded 2 by 2s. Exactly the same logic works in this cell, and the logic works doubly in this cell because it's applying to the row and the column. And exactly the same logic applies to 3, 4, 5 and 6, so we can rule all 4 of those digits out of all of the corners, well, these 3 anyway. We can also rule 2 and 7 out, but they are slightly special cases, because you could argue that we could put our 2 shaded cells here and here, and that way, yes, we do have lots of unshaded dominoes, so we can't put a lower digit here, but we can now put a higher digit here because we don't have any shaded dominoes. But the implication of this from the Yin Yang perimeter rule is that all of these become shaded, and now these two cells must both be 9 to describe the number of shaded cells in their column. Similarly, if we tried making this a 7 and kind of separating the unshaded cells from each other, these would all be shaded, those would be unshaded, then the yin-yang implication of that is that these all become unshaded, and now these two digits must both be 0, which is perhaps even more ludicrous than both of them being 9. So all of a sudden, we've whittled the options down for these corners to 1, 8 and 9. And we can also prove that this is not an 8. If this is an 8, then this cell's coordinates are 8, 8. 8 plus 8 is more than 10, so this becomes a shaded cell. We know we need one unshaded cell in here and one unshaded cell in here to make the count of shaded cells correct, and the only way to join those up around the perimeter without breaking this yin-yang rule is by putting the shaded cells there and joining them up like this. Sorry, the unshaded cells there and there. And that way those two digits both have to be 0, which is not allowed. So we can rule 8 out as a possibility there. For exactly the same reason, we can't have both of these being 8, because again, this would be shaded, and the only way to connect up the one unshaded cell in here and the one unshaded cell in here would be to put them like this, and then this cell would be a 0. Now, let's return to these points up here. A row or column with at least one shaded domino cannot go next to a higher row or column, and then vice versa for unshaded dominoes. Well, if we try and put 6 or more shaded cells in a row or column, then we will always get at least one shaded domino. So 6, 7, 8 and 9 in column 1 and row 1 must always go next to lower numbers. Similarly, if we try putting 3 or fewer shaded cells in a row or column, then we will always get at least one unshaded domino. So in that sense, 1, 2 and 3 are all low numbers that must always go next to higher numbers. So what about 4 and 5 then? Well, 4 is almost always low in the sense that we almost always have at least one unshaded domino if we try and put 4 shaded cells in a row or column. But it can be a middle digit if it's arranged exactly like this, with unshaded cells here and shaded cells here. In this way, we don't have any shaded dominoes, and we also don't have any unshaded dominoes. So we can put whatever we like in these cells, high or low, and in that sense 4 can act as a middle digit. We can say a very similar thing about 5. In the case of 5, 5 is almost always a high digit in the sense that we almost always have at least one domino of shaded cells. But if we arrange the shaded cells exactly like this, then we avoid any shaded dominoes, and we also avoid any unshaded dominoes, so 5 can effectively be a middle digit that can go next to high numbers or low numbers. So what we'll find along row 1 and along column 1 is that the high digits, 5, 6, 7, 8 and 9, must always go next to low digits, 1, 2, 3 and 4, in a kind of oscillating pattern like this, unless we are able to use 4 or 5 as a kind of middle digit in one of those exact configurations that we just discussed. And in that case, that green digit, the middle digit, can go next to whatever it likes, so that could be a high digit, and that would make that low, and it would reverse the polarity of the oscillation all the way along the row or column. So we can now go back to this digit and ask whether it can be a 1. Now we know from our original logic that there is either going to be a 9 here or here and here. So by putting a 1 there, we are displacing 9s into these positions. And this will give us this particular arrangement of shaded cells and then unshaded cells just here. Now along row 1 and indeed along column 1, the polarity of the oscillation must reverse at some point, because we've got high, low, high, low, high, low, high, low. Oh dear, that's not a high digit. So at some point along this row and indeed along this column, we need to have a 4 or a 5 acting as a middle digit in order to reverse the polarity of the oscillation. However, you may notice that all of these are unshaded and all of these are shaded. But for the 4 to be a middle digit, we needed unshaded cells in all of the odd positions. Well, that's not the case because we've got a shaded cell here. And for the 5 to be the middle digit, we needed shaded cells in all of these positions. And that's not the case because we've got an unshaded cell here, and that applies all the way along here and, of course, in the columns as well. So, in other words, we need to reverse the polarity of the oscillation along row 1 and along column 1, but we never have an opportunity to do so because 4 and 5 can never act as middle digits. So we now have a digit in the grid that cannot be a 1, so it must be a 9, and that means that all of these become shaded. Now, before we return to our original grid, let's just milk this logic for all it's worth, because we can also say these can't both be 1s, just like we used the same proof that this can't be an 8 to prove that these can't both be 8s. Again, if these are both 1s, then this pattern of unshaded cells happens, and then we get the same problem. We need to reverse the polarity of the oscillation along row 1 and along column 1, but there are never any opportunities to do so because the 4 and the 5 cannot work in their particular configurations that they need to in order to be middle digits. So what we know then is that this is effectively a 1/8 pair. We can also unshade this because we can't have a 2 by 2 of shaded cells, and we can also unshade this because whichever way round these two digits go, 1 and 8, we know they must be a 1/8 pair. They can't both be 1s, they can't both be 8s, and 1 plus 8 is less than 10, so that coordinate must therefore be unshaded. This will apply to every puzzle you play with this particular rule set. So we can now go back to our original puzzle and input that knowledge. So these all become shaded, this becomes unshaded, this becomes unshaded. This is no longer going to be a pair of 9s, it's going to be a 1/8 pair, and of course we can finally input our first digit into the grid, which is a 9. So we have finally revealed a clue that is unique to Foghqwhgads, and it is this balancer line just here. Now this is where the clarifications at the bottom of the balancer line paragraph come in handy. It tells us that the line does not branch off like that or anything like that, and it's also not two separate lines that happen to intersect, because if it was, then they would need to be different colours, and they are both red. So it is this particular configuration, which tells us that these 3 cells must sum to the same as this 1 cell. Well, what's the lowest that we can make these 3 cells? And it's not 1, 2 and 3, because we need at least 1 high digit in here. We can't have 2 low digits next to each other in column 1. So the lowest we can actually make it is 1, 2 and 5, with a 5 in this domino to pair with the low digit. That's also the highest we can make it, because if we made it any more, then this digit would be at least 9, and it can't be 9 or above. So this is an 8, which has revealed the rest of box 1, which we can fill in as 3, 4, 6 and 7. Now at this point I've just spotted a slight ambiguity with the rules. Based on what we can see, it might be possible that this red line extends downwards and is just completely hidden by the purple line that also extends downwards. That doesn't happen, but I think before we publish this puzzle I might just add one more line in the rules just to clarify that nothing like that could happen, and indeed this red line does stop here. Knowing that, we can say that this must be 2 cells summing to the same as another cell. We don't know which ones are going to be shaded or unshaded or anything like that, but it must be 2 digits summing to 1 other digit. It can't be 3 digits summing to 0 other digits. So we need, from our selection of 3, 4, 6 and 7, 2 digits that will sum to 1 other. So it must be 3, 4 and 7, which gives us a 6 in here. At this point there is a bit more shading we can do, which isn't entirely necessary right now, but it just saves a bit of time later. If this cell is a 1, then all of these become unshaded. If this cell is a 2, then that means there's a 1 in here, making this an 8, and now the only 2 shaded cells in this column must be where the coordinates are 2 and 9 and 2 and 8. So in either of those versions of the world, these all become unshaded. we can say a very similar thing about row 2, except there is one other possibility, which is that it's a 5. And if it is a 5, then in order to avoid any 2x2s with this 9 row, then the 5 must be spread out exactly like that with the shaded cells. So again, in all of those 3 versions of the world, these all become unshaded. We actually knew this had to be unshaded anyway because we need something to balance out whatever this sum is. We now know that this is 6 plus something, so it's more than 6 and it can't be 8, so it's 7 or 9, which means this is 1 or 3. But if we made this a 1, then that would put a 1 in there, meaning that this can't be 1 and also this can't be 1. But we know one of them needs to be a 1, so that cannot be a 1. It is in fact a 3, which makes this a 9. And we can also say that whatever this digit is, whether it's 1, 2 or 5, when you add 3 to it, it will definitely be less than 10, meaning that this cell is definitely unshaded. Now, the next step is quite awkward, but I'm hoping that it's very clear what the most powerful question that you can ask at this stage is, and then it's just a little bit fiddly actually answering that question. That question is, can this cell be shaded? So let's make it shaded. We now have a very similar situation over here to the one that we had over here, where this must be a minimum of 1, 2 and 5. The 5 actually has to go exactly there to avoid 2 low numbers next to each other. This would be a 1 and a 2. This can't be as high as 9, so it is forced to be exactly like this. And then hopefully your intuition will tell you that we basically just don't have enough shaded cells for connectivity purposes in these 3 columns. Or there is another way to think of it, because once you've got this, we can actually fill the rest of this row in with 8, 4 and 7 like this, and now your intuition might be telling you that we have too many shaded cells in these 3 columns. It's a little bit hard to then go on and prove that that's the case, but I will do that now with these 3. This being shaded implies that this has to be a 5, so that the coordinates add up to at least 10. And now somewhere along here there is going to be a 6. And wherever we put that 6, it will have 2 low digits next to it. And even if they're as high as 3 and 4, these will form effectively rungs of unshaded cells, because 3, 5 and 1 and 2 will always add up to less than 10 when paired with a 3 or a 4. 3 and 6 adds up to less than 10, 1 or 2 and 6 adds up to less than 10, and 5 and 6 adds up to more than 10. So that becomes shaded and it becomes completely isolated from its friends, which breaks Yin Yang. So it is a little bit awkward to prove, but it is very much possible to prove that this cell is not shaded. And as soon as we do that, that's huge, because there are now only 4 potential shaded cells in this row, meaning that cannot any longer be a 5, and we can place a 5 just here. Now that we've got a 5 here, 5 plus 6 is shaded, more than 10. 1 or 2 plus 6 is unshaded, and we know that the 2 of one type of cell must add up to the 1 of the other type of cell, so this must now be the 7, and these 2 are a 3-4 pair. We can do a bit more shading at this juncture. For exactly the same reason that we said all of these are unshaded, we can now unshade all of these. We can shade this because we want to avoid a 2x2 of unshaded cells, and we can also shade this because this shaded cell needs to escape. And now that this is shaded, the implication is that that plus 6 is at least 10, so that must be at least 4. Now we can ask, can this be shaded? If this is shaded, that's telling us 2 things. It's telling us that these 3 digits sum to that digit, but it's also telling us that 3 plus whatever that is must be at least 10 to make that shaded, so this must be a 7 or an 8. And now that it's at least 7, whatever we put into here is not going to add up to a single digit total. If we put that 1 and 2, if we make that 1 and 2 plus a 7, that's going to be at least 10, so that does not work. We cannot make that shaded, so we do have to make it unshaded, which therefore implies that this is not 7 or 8, so it must be 4 or 6. Now, this shaded island still needs to escape, so that implies that's shaded, and now we can look at this cell, which must be high enough that when you add 6 to it, it will equal at least 10. So again, it is 4, 6, 7 or 8. These can't both be high digits, so one of them must be a 4. So we can now ask, Is that a 4? Well, we've clearly got a purple balancer line that goes here, two unshaded cells summing to the same as two shaded cells. So this is 4 plus something. So if we made that 4, then it must be 4 plus something, and we'd get two somethings in the same box. So that is not a 4, it must instead be a 3. If this is 4 and 6, then that's 10, so that would need to be 3 and 7. If that's 4 and 7, that's 11, so this needs to be 3 and 8. Well, it's clearly not that, so that cannot be a 7. And if it's 4 and 8, then that would need to be 3 and 9 to sum to 12. Of course, we can also use this 3 to make that a 4. Now, we can't make this an 8 because an 8 here puts a 1 here, and that means the oscillation doesn't work anymore. High, low, high, low. Oh dear, that being a 1 breaks the oscillation, so we would need to have a middle digit somewhere along here to reverse the polarity of the oscillation, but we can't do that because the only middle digit we can use is a 5, and that's already taken for the column. So this is no longer an 8, which means that the 4-6 pair sums to 10, so we need 3 and 7. Now that we've kept this cell down to a maximum of 6, when you add 3 to it, it's going to be less than 10. So again, we can unshade this, and again, we can say that this island of shaded cells needs to escape, and again, we can say that this cell must be at least 4 again, so that when you add 6 to it, it becomes at least 10. Except this time, it can't be 4 or 6, or 5, or 9, or 7, so it must be 8, and that's going to blow the entire puzzle wide open, because that puts a 1 there and an 8 there, because we knew that was always going to be a 1-8 pair. Now that we've got a 1 here, we can put a 2 here, we can put a 1 here. In order to complete this column, we need 3 and 7, but we can't have two high digits next to each other, so that becomes the 3, that becomes the 7. Again, we can't have two high digits next to each other, so that becomes 4, that becomes 6. This row is just going to oscillate between high and low now, so these are the two remaining high digits, these are the remaining low digits. Now we can have a look at this balancer line and ask what's the highest that we can make this digit. Well, it's not going to be 9 or 8, so it's a maximum of 7. And what's the minimum that we can make these two digits? Clearly a 5 and a 2. So 5 plus 2 is 7, so that is exactly what it must be. 5 there, 2 there, 7 there. That 5 makes that into a 7, and the 2 makes that into a 4. And all of a sudden, we have completed all 17 of these digits, which means that we can fill the whole of the rest of the shading in based on the coordinates rule, or just the standard filler rules, a little bit like this. Hopefully you'll agree this obeys all of the laws of Yin Yang and filler, so we've now completed those parts of the puzzle, and it's just balancers and normal sudoku to go. Let's start with this balancer line. This sums to 11, so we need these to sum to 11. They can't be 7 and 4, they can't be 8 and 3, they can't be 9 and 2, so they must be 5 and 6, and this 5 tells us which way round. Now to complete this box we need 1, 2 and 8, but the 2 and 8 here tells us that that's going to be a 1. Now to complete this row we need 3 and 6, and in order to complete this row we need 1, 4 and 9. Now we've got a funny W-shaped balancer line here, which is telling us that this cell is the sum of all 4 of these. Now if we try putting anything other than 9 into that cell, that's going to break horrendously, so that is a 9, meaning this is a 1-4 pair, which sums to 5, so we need these two to sum to 4 in order to correct the balance, so they must be a 1-3 pair. We've now got an X-wing on 3s, telling us that the 3 in this column must go down here, except it's not just here because of that 3. We also have an X-wing on 1s, telling us that the 1 in this column must go down here, except it's not here because of that 1. So that's done. Now we can look into the bottom left corner. These 3 cells, according to this balancer line, must have the same sum as these 3, which is 11. The lowest we can make them is 2, 4 and 5, and that does indeed sum to 11, so that's what they must be, meaning that the remaining cells are 6, 8 and 9, and that 6 tells us that that must be the 6, and this is an 8-9 pair. Now this balancer line means that the only option left for these cells is a 9 here, an 8 here, and a 1 here. That 1 is what knocking a 1 out of there and putting it into there, which knocks a 3 out of there and puts the 3 into there. Now we can look at this balancer line. Over here, green is 1 less than yellow, so over here, to correct the balance, green must be 1 more than yellow. Well, the raw options for this cell are not 1 and 3, not 4, not 6, 7, 8 or 9, so it must be 2 or 5, so this must be 1 less, which means 1 or 4, except it's not 1, so that must be 4 there and 5 there. Now to complete this row, we need 2, 8 and 9, except this is not 2 or 9, so it's an 8. And we get a 2-9 pair here, which forms an X-wing on 2s, with these 2s here, meaning that in this column, the only place for a 2 is down here. We also have a 4 and a 5 in this column, making this a 2, which actually tells us that is our 2. And these are not 2s. I've labelled the remaining fog cells with an F in the corner just because these slightly darker colours aren't particularly distinct from the slightly lighter colours around them. Right, let's look at this balancer line, which clearly picks up at least 3 unshaded cells. Well, those unshaded cells cannot include 1, 2 or 3, so it must be a minimum of 4, 5 and 6, which sums to 15. So we must collect at least 2 shaded cells to correct that balance. So the line must travel up here. That's 1 unshaded cell. It can't go either side, because if it did, we'd be able to see it. So it must continue straight up, therefore collecting another unshaded cell, which also can't be 1, 2 or 3. So now these 4 unshaded cells are a minimum of 4, 5, 6 and 7, which sums to 22. So we now need to go and collect another shaded cell. What's the maximum we can make the shaded cells? That's not a 9, so that's a maximum of 8. This is a maximum of 7, because it can't be 8 from that 8 there, and it can't be 9 from the 2, 9 pair here. So we've now got a score of 15 for the shaded cells and 22 for the unshaded cells, so we still need to collect more shaded cells. Can we collect this 9 over here in the shaded cell? Well, if we do, let's draw the line up like that, then that's going to bring us to a score of 24, potentially, for the shaded cells. But in doing so, we're collecting another unshaded cell. So we've got 22 in the unshaded cells so far. If we can keep this down to 2 or 1, then this is going to be a valid line. But it can't be a 1, and this 2-9 pair tells us that it's not a 2, so it is a minimum of 3 just there. And therefore the unshaded cells will still be beating the shaded cells, and that does not work. So we cannot travel all the way up to there. We must instead turn right just here, and as soon as we turn right, we are intersecting with this line segment that is clearly going into this cell, and because they are the same colour, we know that they must be the same line segment, and that therefore is exactly how that line resolves. So what's the maximum we can put in that cell? Well, we can actually put 9 there. And what's the minimum we can put in that cell? Well, it's not going to be a 1, so the minimum is 2. So the minimum of our unshaded total is 22 plus 2, which is 24. And the maximum of our shaded total is 7 plus 8 plus 9, which is 24. So we have no degrees of freedom. There's no possibility for wiggling the line at all like that. We have proved conclusively, because there are no degrees of freedom, that it must be exactly like that, and it must be exactly the extremes that we've just proven, because we have no degrees of freedom. This must be a 2, this must be a 9, this must be a 7, this must be an 8, this must be a 4, 5, 6, 7 quadruple to add to 22, and we have now completed all of the balancer line logic. The rest of it is just normal Sudoku, which can be completed like this. Please let us know how you got on in the comments and leave a like on the video, and thank you very much for watching.